We'll wait for a few minutes for others to join. All right, so welcome everyone to the week 3 tutorial of fluid mechanics. Am I audible? Can anyone of you confirm? Afros, am I audible? Saurav?
Yes, yes.
Yeah,
Yes,
okay,
sir.
okay. Great, great. Okay. So I hope you all have been regular to your uh, assignments as well as watching the videos on the NPTEL portal by the professor. And those who have missed or wanted to revise, they might have seen my tutorial videos as well, which are uploaded on the YouTube. I expect that everyone have uh, been able to watch have received the first of all the mail from the NPTEL regarding the recording sheet, and they are able to access the PDF notes of the last tutorial. So in last tutorial, our last topic was related to the speed of sound, okay, where we discussed about the incompressible fluid behaviors. So if the Mach number is less than 0.32, even a compressible fluid can behave as an incompressible fluid. Okay. So today we will start with next topic, that is surface tension. Very important topic again. Let me share my screen. I hope my screen is visible now. Okay. So just start. So the topic is surface tension. Surface tension. So what is a definition of a surface tension? What in a short answer, what we can say, it is that surface tension is nothing but the tendency of a liquid surface which is at rest to shrink it to the minimum surface area as possible. Okay. So in a layman term, let me explain step by step that what does a surface tension basically means to realize you in a physical sense. So suppose you have a layer of a fluid. Okay. So you have a layer of a fluid, and inside this is a liquid. Inside it is a liquid, and outside it is a gas. Okay, outside this layer is a gas. So it's a liquid. Whole of the fluid below this line is the liquid. So eventually there will be liquid molecules. Okay, so let us say some molecules are here, liquid molecules are here. Okay, all right. So some of the liquid molecules are like this, whereas some of the liquid molecules will be here as well at the interface of the gas and liquid, of the gas and liquid. So if I observe this particle A, what can I see? That in the liquid itself or any fluid, there are cohesion forces. That is the force in the same fluid because of the presence of the other molecules on each other. So this is the cohesion force acting on particle A because of the above fluid particle. Similarly, from the left hand side, from the bottom side, and from the right hand side. Okay. So what we can say that this fluid particle is in an equilibrium state, that it is surrounded by the equal amount of forces acting over that fluid particle. Okay. There will be more than that particles. Just for the demonstration part, I have taken just 4 particles surrounded by A. Okay, surrounding the A. And there will be another particles on the surface of the interface, basically of gas liquid interface, that is the B. Let me use some other color. So this is B. Okay, the particle B. So now you observe that there are forces from the left hand side on the B, from the right hand side on the B, but as well as there will be from the bottom side of the B as well. So if I draw like this, so from here if particles are there will be the forces acting here as well. But there is no particle above this interface in the gas on the gas liquid interface. Okay. So what does it mean? There is cohesion forces, cohesions or the intermolecular forces between the liquid particles, but there is an unbalanced force which is acting. There is an unbalanced force which is acting because of the gas particles are trying to attract or you can say pull it towards themselves or to the liquid particle B by the gas particles. Okay, so that means there is an adhesion because there is two different fluids are acting. So whenever there are two different fluids or two different states of matter, then it means that there are adhesion between them. Okay, whereas if there is same fluid, then the particle inside that fluid are are having a forces of cohesive forces inside them. Okay, so at the interface there is a adhesion between adhesion between between gas between the gas and the particle B and particle B. Okay, there is an adhesion force, whereas there is a cohesion force which is unbalanced in nature at the interface. There is a cohesion force. Let's use this cohesion, and this is nothing but unbalanced because attraction of or the pull of the gas particles to the particle B is lesser compared to the cohesion forces between the molecules. So this kind of attraction at the interface between the cohesion and the unbalanced cohesion and the adhesion between gas and particle B is nothing but a force which is acting that is nothing but sigma, and we denote the sigma as surface tension. All right. So this surface tension is only due to cohesion. This surface tension is only due to cohesion, as adhesion is only responsible for surface tension intensity. Okay. Surface tension is only due to cohesion. I'll write here. Just hold on. Yes, any doubt? So surface tension only due to cohesion. Yeah, does anyone have any doubt? If not, please keep your mics on mute.
Sorry, you are mute. Please unmute.
Hello, am I audible now?
Yes, yes.
So were you able to listen so far what I was explaining?
No, sir.
So anyone of you should have told me. All right. Okay, thank you for pointing it out right now, Kapil. Uh, I again explain. I was talking. If I am mute or some technical glitch happens, please immediately tell me. Okay, so I was explaining the surface. We have started with the topic of surface tension. Okay, in the last tutorial we have done till the Mach number scenarios where for a Mach number less than 0.32, the fluid behavior was studied. Okay, so in today's surface tension, what surface tension basically is? So surface tension is nothing but tendency of the liquid surfaces at rest to shrink into the minimum surface area as possible. So in layman terms, we can say that if we have this gas liquid interface, gas and liquid interface, okay. So there in the liquid, there are molecules of liquid, these molecules as you observe, okay. These are the molecules as you observe. Suppose we have taken a molecule A of the liquid, and in the surrounding, which is surrounded by the neighboring liquid molecules. So on the liquid particle A, the forces are acting. The forces are acting on that. So this is nothing but a balance system. So from the left and right, top and bottom, the forces are equal in equal amount, and this is a balance scenario. Whereas the particle B, which is at near the interface, is having a force because of the left fluid particle, right fluid particle, and the particles which are below. So these intermolecular attraction is nothing called as cohesion, but the particle B is experiencing an unbalanced cohesion forces because of the top fluid is gas instead of the liquid. So there is an unbalanced scenario. The force amount won't be equal. So that is why adhesion is happening between the gas and the particle B. And this leads to an unbalanced cohesive force scenario. And surface tension is nothing but happening because of the cohesion forces, unbalanced cohesion forces as adhesion, whereas the adhesion is nothing but the interaction of between the two different liquids, or you can say fluids. Okay. So instead of this gas, there can be another liquid, oil, water scenario, or water air scenario, water argon scenario, water helium gas scenario. And this, depending on what kind of liquid here it tells us about the intensity of the adhesion force. So if argon is there instead of air, there can be another kind of different kind of force, different intensity of the force compared to the air scenario. Okay. So surface tension is nothing but is due to the unbalanced cohesive forces. It is liquid-liquid or liquid-gas interfacial phenomena. Whenever there will be an interface between the two different fluids, then surface tension is definitely going to act. It is observed at the liquid interface because there is a presence of unbalanced cohesive forces at the liquid interface, and it is defined as surface energy per unit area, or in another term, it can be also defined as a line force, which is nothing but force per unit length. And that is the normal force, which is to the line drawn at the liquid interface. Okay, let me first write it down, whatever I've explained here. Yeah, someone has asked that where can we get the previous recording. So it is on my YouTube channel, as well as the NPTEL team might have mailed you the recording sheet. So in the recording sheet, there might have come a feedback form, and below in that mail, there is a recording sheet. So there are links of all the tutorial session by me as well as by other TAs as well. So if you want to see my, you are attending my, I highly prescribe that you see my tutorial if you have missed. So my name is there, and you can see the link, as well as my YouTube channel is there, which is nothing named as NPTEL with Varnit. I'll write towards the end as well. You can find out the recordings of all the tutorials as well as the PDFs in the video descriptions. All right. So what is a surface tension value? Surface tension value of water and air scenario. Surface tension value of water and air scenario is nothing but 0.073 Newton per meter. This is a very standard value. As well as surface tension of Hg and air scenario, if liquid is mercury instead of water, so it will be 0.49 Newton per meter. As I said, that if the fluid is changed, then the adhesion forces will be responsible for the intensity. Adhesion forces are responsible for the intensity at the surface. So that is why water air has a lesser surface tension compared to mercury air scenario. Okay. All right. So surface tension, let me write here, surface tension. So let me first take one more example to give you a more clear explanation. So if you have a fluid layer here, okay, and if a needle is kept on that fluid layer, you have a fluid layer, if a needle is kept on the fluid layer, this is a needle. This is a front view which you are observing. Okay, this is a needle. Okay. All right. So what does it look from the isometric scenario? Isometric view scenario is that your fluid layer is nothing but like this, and the needle is like this. Needle is kept like this. Okay. So there is surface tension force acting like this between the molecules at the liquid and solid interface, the solid needle and the liquid interface. Okay, this is your needle itself. Needle. Okay, so equivalent of this, how can you observe that? Because there will be some depression, which is very less depression at the meniscus or at the interface of this liquid. So this can be also observed like this. So your fluid layer was initially horizontal. When you kept the needle, there will be a slight depression on the liquid interface. So your needle will be at here, and the surface tension is perpendicular to that needle because of the molecules are attracting, cohesive forces between the molecules of the liquid is acting. So this is your surface tension value at the interface. A slight depression is there, and there will be two components One is the vertical component of the surface tension force, and one is the horizontal component of the surface tension force. Okay, vertical and horizontal component. So if your angle, this is theta, this is angle theta. So this will be nothing but sigma sine theta. Sigma. Oh. So surface tension is, let me write in a mathematical form. Surface tension is nothing but surface energy per unit area. So if it is defined in this term, then your unit will be joule per meter square, or it is also defined as surface tension is force, surface tension force per unit length. Okay, if per unit length, and here unit will be force as a unit of Newton and length as a unit of meter, Newton per meter. So this Fs is nothing but your surface tension force. Surface tension force. Okay. All right. So let me write the definition. Surface tension is tendency of liquid surface at rest to shrink into the minimum surface area possible. Minimum surface area possible. Surface tension is due to unbalanced cohesive forces next. It is liquid or liquid gas interfacial phenomena it is observed. The surface tension is always observed at liquid interface. It is observed at liquid interface it is defined as surface energy per unit area. Okay, it is defined as surface energy per unit area. Also, it is defined as line force. Line force. And what is this line force? That is expressed as force per unit length that is normal force to the line drawn at the liquid interface. That is normal force to the line drawn at liquid interface. What do I mean by this? Is that Then we had a scenario, this was a liquid interface. This was particle B. Okay. Then there was a neighboring particle. There was a neighboring particle. This was the surface tension force. This was the surface tension force sigma. Okay. Normal drawn to the line drawn at liquid interface. So if I draw a line from the interface like this, where needle was kept, if this was a complete needle, so this is the line drawn and the surface tension is perpendicular. The surface tension is perpendicular. This surface tension is perpendicular. Okay. All right. Next point. As the temperature increases, surface tension force decreases. Why? Because cohesion intermolecular forces decreases. Cohesion force decreases. This implies, therefore, surface tension decreases. Okay. If you add any detergent or surfactant in a liquid, okay, then the surface tension also decreases. Or if you add salt in the liquid, then surface tension increases. Okay. By adding detergent, surface tension decreases, and by adding salt, surface tension increases. Where these can be applied? What are the applications? Is like capillarity scenario, soap water, sap water in trees. Okay, so in the trees, how the water lift up? It's because of the surface tension capillarity phenomena. Floating of leaves at the interface water surfaces. Okay, so what are the applications? Where do you see such phenomena is in capillarity? Next is soap of water in trees. Sap of, sorry, I'm saying soap. Sap of in trees. Okay. Floating leaves on water surface. All right. So we have defined surface tension using two concepts. One is surface energy per unit area, another is surface force per unit length. I'll explain both ways, okay, in both the ways. Any doubts still here to anyone? Yes or no? I want answer from everyone.
No, sir.
No doubts? Okay, great. Now let's explain the surface energy concept. So this is a very common experiment which you will see in your fluid mechanics labs in your colleges or universities or institutes, that there is a frame which is dipped in a soap solution and one end of the frame is movable whereas other three are arrested. If you dip that in the soap solution and take it out, and if you try to pull the one end of the lever which is movable on that frame, you will see that soap film is increasing and it will stretch out to some extent. After that, it will burst. So what is happening basically there is that there is nothing but surface tension of the soap liquid interface is balancing by the force which you are applying to pull it. Okay. As soon as the force or the stretch is maximum, then that there is an unbalanced scenario. where your force has exceeded the surface tension force, and the bubble, so not bubble, soap layer sheet will break. This you will see such kind of experiments or on the internet as well. You can check out. So I'll make a experimental frame of this. So it looks something like this. So this is a frame. So this lever is movable, whereas other three are rested. So there is a liquid layer, soap bubble fill till here. Not soap bubble, my mistake. So solution thin film. Okay. And you are applying a force F on this lever. You are trying to pull this lever slowly and slowly, not fast. Otherwise, it will immediately break. So this lever is movable. You are applying a force. You have stretched it to some scenario till here. Okay. This lever till here. So what has happened? Fluid layer has also stretched till here. So solution fluid layer is also stretched. So until when the energy state was E1 till here, when it was not stretched. When it was not stretched, the energy state scenario was E1. There was some energy stored there. Okay, let us suppose it is called as E1. Okay, when you have stretched it, then the energy stored has increased in some form of potential. Let us say it is E2 till here. And you have displaced this solution by delta x. Suppose this is your delta x you have displaced. So outside the soap solution, there is air. Outside this system, there is air. So what has happened? There is an increase. So let us suppose this length of the lever is length L. Length of the lever is L. Okay. So how much you have increased the area? Can anyone of you tell me? You know the dimensions. What is the increase in the area? This is, huh? What is the increase in the area? It's a rectangle. What is the formula of area of a rectangle? This is your increase in the area, right? So tell me what is the increase in the area?
L into delta x.
L into delta x. Okay, great. So total increased area is total increased area is nothing but length into width. That is delta x. Delta x is your width and length is this. The length into width is your area of a rectangle. So it will be L into delta x. But can you physically feel this scenario that this is a frame system and above is also air and below is also air. So it is not the top layer of, it is also the bottom area. So this is a thin soap sheet, liquid sheet, which is surrounded from the top side from the air as well as the bottom side also. So increase is above area as well as below area. So it will be 2 times L into delta x. 2 times L into delta x. All right. So this is your liquid membrane. Liquid membrane. Are you all able to understand that why the total increase area is 2 times of L into delta x? Because there is a upper sheet is there, which is in the interaction, whereas below side is also in, which you can't see from it. Okay. So 2 times L into delta x. Now you tell me, what is the work done to create increased area? You have increased this, so you have done some work on the system. okay, which is nothing but work done, which is stored in the form of surface energy. Okay, that is E1 E2. That is E1 E2. So work done to create increased area is nothing but work W is, what is the formula of work done? Force into displacement. Force into displacement. Force into displacement. Now this force is nothing but in the terms of line force. This force is nothing but force which is in the terms of line force. So we know what is the definition of surface tension in terms of line force. It is nothing but, since surface tension is also defined as force per unit length, per unit length. Okay, from the other definition. So force will be sigma into L, sigma into L. So this was your force and this is your L. Both are perpendicular. Okay, and here the surface tension is acting. Here the surface tension is acting. Now you will be easily able to observe where I am saying here. This is the surface tension force acting over perpendicular. This is your sigma line force. F is your line force. Okay. And it is not L, it will be 2 times of it, upper layer and below layer. So that will be 2 into L into sigma into delta x. This is your 2 sigma L delta x. So this is sigma, if you take out, it will be 2 times L delta x. And 2 delta x is nothing but your increased in area. This is your increase in area, 2 L delta x. So that can be said as delta A. Delta A. Sigma into delta area is your work. Is your work. So surface tension is work done per unit area, and work done is nothing but energy. Work done is nothing but form of energy. There are 2 forms of energy which you will study in thermodynamics: heat and work. Heat and work. Heat is because of the presence of temperature difference, and work is because of the mechanical presence of the mechanical forces. So work done per unit area. This is nothing but your energy. This work done can be written as sigma into delta A, and delta A is nothing but sigma into area one final minus area initial A2 minus A1. So sigma A2 minus sigma A1, and this was your E2 which I wrote, stored in some form of energy, E2 minus E1. This was your work done. This was your work done. This was E2. This was E1. Okay. E2 minus. So this is your final surface energy. Final surface energy, and this was initial surface energy. Initial surface, and this is having more energy. This state E2 have more energy. This state has more energy. You can physically feel that when you have stretched something, so some amount of energy will be stored more, okay, which is unbalanced in nature. Suppose you stretch a rubber band, you will feel on your hand that some energy is stored while you are stretching it. Okay, when you will release, then energy will be less. Release the rubber band. So there is an unbalanced form of energy. So it is an unstable scenario. As soon as you release it, it will go back. This state has more energy. Therefore, it is unstable in nature. Stable in nature. Any doubts till here? Understanding this experiment? To anyone? If you have any doubts, please ask. Because this was very important to physically understand. Any doubts? No doubts? Yes or no?
No, sir.
Okay. Suppose we take another example where we have a thick liquid membrane. Okay. This was a very thin liquid membrane. Okay. Now we will take a scenario where it is thick liquid. Why we take two multiple here? So I have told this two multiple now. This one you are asking. You can unmute and ask. So this two, I suppose that this is the two which you are talking. So as I explained that this system you are viewing from the top. When you will view it from the front, this thin layer has contact with the upper air as well as the bottom air. So you have increased the top surface area L into delta X as well as the bottom surface area L into delta X. So this is twice the area, the upper layer as well as the bottom, 2L delta X. That is the reason. Okay. Suppose we take a scenario where it is a thickness of a liquid membrane is given to you. Okay. So T is the thickness. Thickness of liquid membrane. And obviously there will be fluid particles. And there will be a surface tension force. Sigma. Not for the internal particles, only the external, that is A and this is A, B, C, D. So only for A and D, because that is only contact. That is the only interface. So only A and D particle will observe the surface tension. So this surface tension, Fs, that is by A and D and not by B and C. By A and D and not by B and C is nothing but sigma into, if suppose length is given to you L, plus sigma into L, the part because of particle A as well as particle D. So it is 2 times is there. First, this is some thin membrane, okay, which will have some thickness. So that is why it was 2 times sigma L. Okay, 2 sigma. Okay. Now you are able to understand this factor too. All right. Now it is much evident when you have seen in your childhood that there is one vendor which blows a balloon from the soap solution. He just blows an air in a circular ring which is dipped in the soap solution. When it blows the air, it forms into a bubble. Have you ever thought that why that bubble is always spherical in nature? Whatever shape that frame is, even if it's square shape, triangle shape, star shape, the bubble will eventually come out in the form of, when it will detach from that frame, it will be in the form of spherical shape, always. Okay, it doesn't matter that what is the shape of the frame. So what is the reason behind is that because sphere is of minimum, sphere geometry has minimum surface area compared to conical, cylindrical or any other geometry. Sphere geometry has the minimum surface area. So if minimum surface area is there, and what is the surface tension definition? It is the tendency of the liquid, that is the soap solution bubble, and the air liquid at rest to shrink to the minimum surface area as possible, so that you have minimum surface energy. Every system in this universe want to achieve minimum energy state. Even humans, if they are lying on a table or a chair or a bed, they would appreciate more to sit and rest compared to work or move. And they want to conserve energy and always be in a minimum energy state. Same, every object or particle in the universe, in the nature, follows this rule. And sphere has a minimum surface area, so it will have minimum surface energy. That is why the soap solution bubbles are always spherical in shape. So I'll write that very important note. For a given volume, V, if you have cylindrical shape or conical shape or spherical shape, okay, all have same volume V. This is sphere, not circle. So sphere will have less surface energy and more stable, less surface energy, since less surface area and is more stable. Okay. Therefore, therefore bubbles droplets are in spherical shape. Okay. So my PhD, which I'm working in IIT Delhi, is on multi-phase flows only, and I'm particularly dealing in droplets and bubbles only. Okay. All right. So a liquid droplet has energy. Suppose I'm a liquid droplet. This is a liquid droplet. Surface tension will be acting on the surface eventually. This is sigma, sigma everywhere on its circumference. So what will be the energy here? Surface tension into area, because surface tension is nothing but surface energy per unit area. Surface tension into area. And what will be the surface area of a sphere? It is pi by 4. Oh, sorry, 4 pi r square. 4 pi r square, radius of the sphere. This is your energy. Instead, if you have an air bubble, this was a droplet. Suppose you have an air bubble. Like this, which has some thickness. Air is there. Okay. Again, there will be surface tension here as well as surface tension here, because 2 times air is there inside as well as outside. And this is your bubble. So here energy E will be sigma into area, and that is, will it be sigma or 2 sigma? Tell me. Will it be sigma or 2 sigma? Unmute and tell me. Will it be sigma or 2 sigma?
Sir, 2 sigma.
Why?
Sir, because there are two layers.
Two layers, yes, correct. There are two layers of interfaces. Okay, two layers. Inside is air and liquid, outside is air and liquid. So it will be 2 sigma into 4 pi r square. Okay, so it is a very thin when you see a air bubble. All right. So if sphere has least area, sphere has least area as sphere has least area A, this implies sigma is high, higher surface tension will be there on the bubble. Okay, higher surface tension, or you can say E, which is nothing but sigma into A. So energy will be less as area is less. So it is less. E is okay for a minimum surface. All right. Now let's come to the next topic. Suppose you have three different kind of interfaces. First interface looks like this. Second interface looks like this. Third interface looks like this. Okay. So in the first scenario, here it is P1 at the left hand side of the interface, and on the right hand side of the interface it is P2. It is balanced. There is no change in the shape. So that means it is saying that pressure on both sides of the interface will be equal. Okay. Whereas if you have a scenario where your pressure P1 is here and P2 is here, by obvious sense we can see that P1 pressure is more and it is trying to push it outside. So that's why this shape is there. So P1 is greater than P2. And if you have a scenario like this, P1, P2, and from here, this easily tells us that P1 is less than P1 is less than P2 for these three different kind of interfaces. Now let's come to very important topic, that is pressure inside liquid droplet or air bubble. Okay, pressure inside liquid droplet. I'll just take a minute of break. You also guys take. I'll just join back in. Okay, all right. So that let us come to the other topic, that is pressure inside. Now we need to evaluate that what is the pressure inside a liquid droplet or a bubble, how we can evaluate. We'll evaluate based on the concept of surface tension. So pressure inside liquid droplet or you can say air bubble. Air bubble. So liquid drop, if you have like this is your liquid drop. There is surface tension on the surface. Okay. It will also look like this also at every point. So I'm just drawing top importance. And it has some pressure P, which you need to evaluate. What is the pressure inside this? How we will get that. So what we will do, we will cut this in a half section and view its half section first of all. So half of the drop will look something like this. Half of the drop will look something like this. The diameter of the drop is this d. D is the diameter of the drop. Now inside this droplet, there is a pressure acting by the fluid at the interface, as well as the pressure is also acting from the outside because of the presence of atmosphere. Okay. So what is happening? There is a pressure which is acting. That is P, which you need to evaluate. Okay. Whereas it is also experiencing outside pressure, that is P atmosphere. P atmosphere. So what is basically the pressure P? Force because of the pressure change in the pressure, because there is a pressure difference. There is a pressure inside. This is a scenario like this, where P1 is greater than P2. So there is eventually a pressure difference. It is not equal. So because of the pressure difference at this interface, there will be a pressure force. There will be a pressure force. So how we will evaluate that pressure force? You will take a projected area of this curve. The projected area of this curve will be nothing but the projected area. If you just flatten out this drop into a single projection, it will look like this. That is your this scenario. This is your projected area. And this projected area has a force of pressure force Fp, and this Fp pressure force is nothing but change into pressure into area, this projected area, delta P into projected area. So what will be Fp? Change in pressure into area. And what is the area of this circle, red circle? Pi by 4 d square. Pi by 4 d square of a circle. This is your pressure force. If some pressure force is there, eventually there is surface tension force also acting on the surface. There is surface tension force also acting. So if I draw this drop again, so there is surface tension force which is acting. That is sigma, 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 sigma. Okay. This is surface tension force. What will be surface tension force? Fs. That is surface tension coefficient into length L. Surface tension coefficient sigma into length L. What will be the length L? By visualization, what do you see that what will be the length L? Force, what is surface tension coefficient? It is surface tension force per unit length. Surface tension force is surface tension coefficient into length. What is the length L? So length L is nothing but your circumference of that projected area, because you are balancing the force on this projected area itself, right? So this is circumference will be 2 pi r or pi into d, because you are balancing the force at this projection area only. That there is a pressure force, this is a surface tension force, and you are trying to balance them, or see that which one is greater or which one is lesser. Okay, so it will be sigma into pi into diameter, sigma into pi into diameter, sigma into pi into diameter. This is your Fs. Now, for the droplet to be in equilibrium state, both the forces need to be equal. Under equilibrium condition, the Fp is equal to Fs. Okay. So what was Fp? It was delta P into pi by 4 d square, whereas Fs is nothing but sigma into pi d. If you just evaluate from here, the pressure difference is nothing but 4 sigma by t. 4 sigma by P. And this is your pressure difference. That is inside pressure minus atmosphere. So pressure difference is nothing but P minus P atmosphere. Because this P was inside and P atmosphere was outside, this was the pressure difference. So P minus P atmosphere is the pressure difference 4 sigma by T. And if it is asked in terms of absolute terms, so it will be P atmosphere plus 4 sigma by. This is your absolute pressure. And this was your change in the pressure. Change in the pressure. If it is said that P atmosphere is 0, there is vacuum outside. Okay, there is no atmospheric pressure. Only there is a balance of inside pressure bubble with that of the surface tension force. So if P atmosphere is 0, this implies the pressure inside bubble will only be 4 sigma. And this is nothing but your gauge pressure. So absolute pressure is always, if you have a reference like this, so this is completely, this is P atmosphere. This is your P absolute, and P gauge is P atmosphere from above the P atmosphere. This is your P gauge. This is your P gauge. And this P gauge is nothing but your 4 sigma. So this is your gauge pressure. We will again draw this in the pressure measurement chapter. Don't worry. I'll explain in detail how this is done. So this is your gauge pressure. So P atmosphere is not given because we are finding the pressure with respect to the gauge, not in the absolute term. And why it does make sense, because P atmosphere can be different for different sea levels. If you are in a Mumbai, city Mumbai, it is very close to sea. Where atmospheric pressure is higher compared to Delhi or Jammu and Kashmir or Himachal, because you are very high above the sea level. So that is why we generally deal in terms of gauge. We calibrate our systems in the labs so that the atmosphere pressure is as per that condition. And then we get the value of the gauge pressure. That's why the gauge pressure is very important. Next is, so here it was pressure inside liquid droplet and air bubble. So liquid droplet you have seen, how does it look like? But how an air bubble will look like, air bubble will also have same value of the change in pressure, but air bubble will look like this. You have a liquid, and under that liquid there is a liquid, air bubble is there. So this is also single surface interface. So it is same as a liquid. Again, this is air, this is liquid. So it is also a single surface interface like the single surface interface here. So both are same. Now let's come to the other scenario of pressure inside soap bubble. So how does a soap bubble look like? I have just framed that soap bubble previously also. So soap bubble will have two interfaces. One and two. Very, very thin. You have seen in the by the vendors who blow soap bubble, as I explained earlier. That is a very thin soap bubble. So here inside is also air. Outside is also air. This is your liquid. Okay. Definitely there are two different interfaces here, outside and inside. So two sigmas will be there. Two sigmas of equal values. Okay. Sigma and sigma. So if two, we have seen the expression for one interface, which is 4 sigma by d. When there will be two interface, it will be 4 sigma by d plus 4 sigma by d. Okay. So I'll not again derive, I'll just write 4 sigma by d plus 4 sigma by d. And this d is same only. You might think that this inside diameter and outside diameter will be different. It is not a thick bubble, air bubble. It is very thin. So it is very thin. So diameter eventually is same. Okay. So that's why we take D. But if you have if the examiner has asked in a sense that there is initial inner diameter and outer diameter, then you have to specifically write there. That is inner diameter 4 sigma by di and 4 sigma by d naught. That is outer. But we generally assume that let di is equal to d naught is equal to d. So it will be the change in pressure will be 8 sigma by d. Okay, in a suburb, suburb. Suppose instead of air inside, I'll again draw suburb. Outside is air. This is liquid, but inside it is, oh, sorry, not helium. Okay, inside it is helium. So if inside gas is different from the outside gas, eventually the surface tension values of inside will be sigma I, okay, or sigma 1, you can say sigma I, and outside will be different. That is sigma out, sigma. So here now your change in pressure will look like 4 sigma I by di plus 4 sigma out by d out. Okay. So if di is equal to d out is equal to d, so the pressure difference will be 4 by d into sigma I plus sigma out. All right, clear this expression. If you have different gases inside and outside, then the scenario will be different for different surfaces. I hope it is clear. Any doubts? Please ask if you have any doubts. Rishika, Saurav, Kartike.
Yeah, no, sir.
Ansi, do you have any doubt? Kapil? Okay, great. Now let's see the third scenario, that is pressure inside the liquid jet. We have seen pressure inside the air bubble or droplet, liquid droplet, pressure inside the soap bubble. Now we'll see pressure inside the liquid jet. So suppose you have a pipe or nozzle, okay, you have used for gardening at your home sometimes to give water to the plants. So the jet comes out of it. Okay. So the jet comes out of it like this. This is your jet. This is your so this is your jet. Okay. So let us suppose we take a section of jet of length L. Okay. Outside it is P atmosphere here, and inside it is P pressure P inside this section. I'll take this section and draw it and do a force balance again. I take this section. Draw. This is the section of length L which I have taken out. Okay. Eventually, P atmosphere is acting from outside. P atmosphere. And inside, again, you will take a projected area as we did for that. So let us say for the cylindrical surface, my projected area is something like this rectangle. Okay. And inside, at this, it will be pressure P. Outside, it is acting P atmosphere. You need to find this P value or delta P in terms of gauge. Okay. So we can observe it very clearly that there won't be any surface tension at this point and this point. Why? Because this is this point and this is this point. So here also there is liquid, here also there is liquid, there is no interface. Interface is only at this point and interface is only at this point, that is this point and this. Okay, physically you are able to understand. So that is why I've written like this. Yes. So no surface tension, no surface tension. As liquid on both sides. In jet. Okay. No surface tension. Now we will see the half section of this jet. We will see the half section of this jet as we did for the liquid drop. So the half section of the jet look like this. This is your half section, which look like this to you. Okay. So there is a force Fp due to the pressure difference. That is nothing but delta P into area. And there is eventually surface tension which is acting at this surfaces. Okay. At the outer, because inside it is a liquid. Inside it is a liquid. Only at the outer surfaces the surface tension is there. Okay, that is sigma. This is the length L. Of this section. So again, you will balance. So Fp is nothing but delta P into area. What is area? This is your diameter. This is your length. What is the area of this rectangle? Tell me. Anyone? What is the area of this rectangle? What is the area of rectangle? Karthike? What is the area of this rectangle? Am I audible? Saurav, am I audible to you?
Yes, sir.
Yeah, so what is the area of this rectangle, Saurav?
LD.
LD, right? Length into diameter. That is L into D. So this was a pressure force. Whereas what is surface tension force? Fs, that is nothing but, again, there are two sides, sigma into L plus sigma into L. Okay. Sigma into L plus sigma into L. From this side and this side. Okay. So twice of sigma L. You will balance them. That is for equilibration, Fp is equal to Fs. So delta P into LD is equal to sigma L. So delta P will be eventually 2 sigma by 2 sigma by. This is your pressure difference for equilibrium situation. Okay, you got the pressure difference for all the three scenarios. That is, in conclusion, we can say delta P is two sigma by d for jet, four sigma by d for liquid drop or air bubble, and 8 sigma by d for soap bubble. Okay, so soap bubble have higher pressure difference. So that means more force is required to make the bubble, whereas jet will form easily. Okay, so that is why you need to push. In nature, you cannot see directly if you don't give any external force bubbles. Okay, directly you cannot see the soap bubble directly. That's why the vendor blows the air at a very fast speed from its mouth, and you also observe that it takes a lot of waviness happens, and then the bubble get exited out of that frame. So it takes a lot more amount of pressure difference. That is, inside pressure should be much higher compared to the atmospheric condition. Whereas jet is easily formed. So at soap bubble, with higher pressure difference, more force is required to make bubble, and whereas jet will easily form. Okay, all right, clear. Now we will come to the concept of wetting and non-wetting phenomena. Wetting and non-wetting phenomena. So by wetting means that any liquid can wet the surface, or a liquid cannot wet the surface, is non-wetting. So suppose you have a glass table, two scenarios I'm framing, both are of glass. On one side of the glass, a water drop is kept. So how the water drop will look like? It will wet the surface. Whereas if you have a mercury drop, it will non-wet the surface. It will be suspended like this. So this is a water scenario. And this is a mercury scenario. Okay. So when adhesive forces are greater than cohesive forces, that means sticking, adhesion is nothing but sticking, okay, is greater than the intermolecular cohesions, then you can say that that liquid will wet that surface. So here in this water scenario, water is sticking to the surface. That is why you are seeing this kind of thing. Okay. So it is sticking to the surface. So here adhesion forces are greater compared to the cohesion forces. Adhesion forces greater than cohesive force. Okay. So that means your forces, there are unbalanced forces as well again. So here adhesive forces are sticking more compared to the inner cohesive forces, whereas in this scenario, the cohesion forces are greater. The the mercury molecules are more strongly bound compared to that of a solid surface. So here, cohesive forces greater than adhesive forces. So this kind of surface, left-hand side, is called as wetting surface. And this kind of surface is called as non-wetting surface. Okay, non-wetting surface. There can be a difference where water can behave as a, water can have more cohesive forces, depend on what is the substrate. Here the substrate was glass. Instead of glass, the solid surface is made of, suppose, Teflon or copper. Then how that liquid will behave on that? So suppose I have, now this is not glass, this is Teflon. Now here the liquid drop will behave as, have more cohesive forces compared to adhesive forces. So this water will behave as non-wetting scenario. Non-wetting scenario. Okay. Or I should have drawn this here, this side.
ये कहाँ कराया है?
Non-wetting scenario. Any doubts? Kapil, any doubts?
No, sir.
Okay. And if I have a substrate that is of copper, then this, if I put a mercury drop here, mercury drop, this will behave as a wetting, Hg. This will behave as a wetting. So here water was, when the glass was there both sides, water was sticking where adhesive forces were more, then it was a wetting surface. Whereas mercury was having more cohesive forces, it was non-wetting surface. But if you put the same mercury on a copper surface, it will behave as wetting. And whereas if you put the water on the Teflon, it will behave as non-wetting. Okay. Now, point to note here is that there is an angle of contact. Angle of contact. Very important topic to understand. From here, we will go to the capillarity. So there is an angle of contact. If you observe, if I draw a tangent from this point, so angle of contact is a tangent inside at the liquid interface up from inside the liquid up to that surface. From inside the liquid up to that surface. So from inside the liquid up to that surface. So this is your angle theta. This is your angle theta. Whereas here, if I draw the tangent at this point, from inside the liquid up to that surface, this is your angle theta. Okay. So this is your tangent. Any doubt? Kapil Kumar, any doubts? You have unmuted.
No, sir.
So can you please mute yourself? And this is tangent. Okay. So both are tangent. So if you observe here, in this scenario, tangent is less than 90 degree. This angle theta is less than 90 degree. So here theta, angle theta is less than pi by 2. Whereas here, if you see, the angle theta is greater than pi by 2. Here theta is greater than pi by 2. Greater than pi. And this angle of contact theta is nothing but tangent from the, is taken from the tangent inside the liquid and up to the surface angle. So in a clean water glass scenario, this scenario, if you have a clean water glass, water is purely clean, there is no impurity inside that, then this will be a flat layer. This liquid will be a flat layer and theta will be 0. But if you have a normal water glass, because of presence of some impurities are there in that normal water, then theta will be some 29 degrees. So I'll write here. Theta for a clean water glass is equal to 0 degree. Normal water is 29 degree. Mercury glass was 130 degree to 138 degrees. Whereas kerosene, if you have a kerosene glass, then it is 26 degrees. So what do we understand by wetting and non-wetting phenomena is? Basically, it is a relative phenomena and it depends on the cohesion between the liquid molecules and adhesion between the liquid surface, liquid and solid surface. Okay. So wetting and non-wetting phenomena is a relative phenomena. It depends on cohesion between the liquid molecules and adhesion between liquid and solid surface. Okay, liquid and solid surface. Now let's come to the concept of capillarity. Very important concept. If do you have any doubts still here? Any doubts? Saurav, Kartikeya,
No, sir.
Kapil, and
No,
Sir.
sir. No, sir.
Okay, great. I'll take a 2 minutes of break and then we'll start with the capillarity topic. Just hold on. Okay, let's come back. It's the topic of capillarity. Very important topic. Let me first write the definitions, then I'll explain. So whenever there is a smaller diameter tube which is inserted into a liquid, then there can be a rise as well as fall with respect to of that liquid in that pipe or the tube with respect to the outer surface. Like you drink uh, soft drinks or some liquid through a straw. So there is an action of capillarity. There is a rise and fall. But for especially capillarity to happen, the tube diameter should always be less than 10 millimeters. Okay. And this rise and fall of the liquid is known as capillarity. Okay. And it is basically because of the presence of cohesive forces. Surface tension is because of the presence of cohesive forces, whereas capillarity is because of the presence of cohesive and adhesive forces. Okay. So let me write first of all the points. When a smaller diameter when a smaller diameter tube of less than 10 mm is inserted into liquid, then there may be a rise or fall of liquid with respect to outer surface. And this rise and fall phenomenon is known as capillarity. Okay. Surface tension happens because of only the unbalanced cohesive forces, whereas capillarity happens because of both cohesive and adhesive forces. Because there is a tube which is solid in nature and there is a liquid. So there is a cohesion adhesion happening. Okay. So surface tension is due to cohesive forces, but capillarity is due to cohesive and adhesive forces. Okay. Now let us understand through a example. Suppose you have a beaker okay, and there is some liquid inside that beaker. You will understand why I've made like this. So I'm making liquid inside this. There is some rise because of meniscus is not perfectly straight. There is always some uncertainty in the meniscus. And if you insert a tube inside this liquid. I should have made this a bit higher. If you insert a tube, okay, and this tube has a diameter d, okay, so there will be some rise as soon as you put the tube. There will be some rise. There will be some rise. Again, their meniscus will be something like this. Your liquid has risen up. There is some rise. So it has risen up by some height h, suppose. It has risen up by some height h, let us say. Okay. There is P atmosphere acting on this liquid because it is open to atmosphere. It is open to atmosphere. If some liquid has risen up here, this is some liquid which has risen. Okay. It will have some weight. It will have some weight. Let us say it has some weight. WT. WT is the weight of the. Now we will draw a tangent because it is wetting or non-wetting. It is a wetting phenomenon. You will understand why. First of all, you draw the tangent from inside the liquid till the surface. So at this point, if I draw a tangent, so from inside the liquid till the surface, tangent to the surface, this theta. This is the theta. Similarly, if you draw a tangent here, this side, this will again be from inside the liquid to the surface. This is the surface and this is the liquid inside. That is the tangent with the angle of contact. Yeah. This is the angle of contact. Now, what is happening? At this point, there is adhesive cohesive forces, wetting is happening, whereas this liquid viscous is open to atmosphere. So there is surface tension also happening. Okay, are you able to feel this? I'll make a bigger diagram so that you can understand. So I'll take a pipe. Only of the pipe. So this was a rise in the liquid. There was a weight acting. There is an angle theta. If you draw a tangent, there is an angle theta from here till here. Okay. And so here it is wetting happening, whereas this liquid meniscus, this is nothing but a cylindrical shell, is experiencing surface tension because this is atmosphere. This is atmosphere. This is open to atmosphere. Right? This is also open to atmosphere. So here, gas, that is air, is there. So surface tension is happening at this point, at the interface, at this point. Similarly, around the whole circumference, sigma, sigma, sigma. That is surface tension coefficient. Now the surface tension coefficient is force will have two components. Surface tension force will have two components. One is vertical, one is horizontal. So one will be vertical and one will be horizontal. So if this angle was theta, so this angle will be theta, right? So this will be sigma cos theta, and this is sigma. I should use that color. Sigma cos sin theta, and this is sigma cos. Similar will happen around whole of the interface. Okay, so all the horizontal components are going to cancel out, whereas all the vertical components are there, which are responsible for the making the curvature of that interface, like that of in droplet or in air bubble, soap bubble, okay, or liquid jet. And this is responsible for wetting, and there is some weight which is acting. So what we will do, we will balance the weight with the surface tension force. These are the forces acting in the vertical direction, because in equilibrium the liquid has risen up and it has reached some equilibrium state up to a height of h, up to a height of, this was a height of h. For under equilibrium, yeah, yes, Kapil. Any doubts? Oh. Under equilibrium, this weight will be balanced by the vertical component of the surface tension force. Weight is equal to Fs. So what is the weight of this much liquid? Weight is nothing but density into volume. Okay, density into volume into G. Weight is mg. Or in terms of specific weight, we can write omega or small w, whatever you want to write. You have understood that specific. That is W into volume. This W is nothing but specific weight. So W into pi by 4 d square, because diameter is d. Diameter of this tube is d. Okay. And on the right hand side, surface tension force component is sigma cos theta. Sigma cos theta into L. What will be the L? The circumference of the whole circle. The circumference of this much, which is acting. Okay. So how it is acting? Let me also help you to visualize. So this is like this. Surface tension force component is acting like this over the whole surface. Right? Correct. That is sigma cos theta. That is sigma cos theta into pi into diameter. Pi into diameter. So that is it. Sigma cos theta pi d. So from here, what you will get? Sorry, pi by 4 d square h. This is the volume. So pi by 4 d square is the area into height. So volume of a cylinder is pi by 4 d square h. So from here you will get the height up till which it has risen up. Sigma cos theta into 4 times pi w. And this is your expression, very important expression. Okay, and you observe that if the diameter decreases, your height increases, the capillarity height. So you have seen the plants have from the roots using the saplings, they suck the water because the water rises up till their height against the gravity is because of the capillarity action. Because the diameter of those small tubes inside the plant or the trees is very less than 10 mm. Okay. That is why it gets up. So now the question might arise that can we reduce diameter very small so that my height will be very high? So there is some also extent up to it will rise. Won't flow outside because Why it won't flow outside? Because there is a presence of surface tension which is also acting on the wetting phenomena. So it cannot be like it will take away outside this tube. It won't take outside that tube. Now you have got the height. If I ask you, any one of you, that what will be the pressure at this point A? What will be the pressure at this point A? The question can come. The pressure at just near to the meniscus, basically. Pressure at this point A. So I want to see what is the pressure just near to the meniscus. Because outside it is P atmosphere, but what will be PA? So pressure at this level is height h. PA plus, if you go down, the pressure increases. That is hydrostatic pressure, rho gh. We will discuss this hydrostatic pressure, don't worry, in the next tutorial. But for now, I'll explain that hydrostatic pressure is density into gravity into h. The height depth, rho gh, is equal to, what was the pressure at this place? Sorry, at this place, if I this diagram, here it was P atmosphere. From there, it was liquid. Oh, so I have done one mistake here while making the diagram. The end is not here. End is more than the tube goes up till here, inside the liquid. Should have made like this. Yes. Because if you observe, height is still this level. This height is still this level. This is P atmosphere. And the tube is inserted more inside. So if I want PA plus rho GH is P atmosphere by pressure balance. So pressure at A plus, if you go below, is equal to rho GH is nothing but your P atmosphere. So pressure at A, which I want to calculate is P atmosphere minus rho GH. And the question comes, where this H will come from? This H will come from. This H will come from. You know what is P atmosphere? You know what is rho of that fluid. You know what is gravitational constant value. You got the H value from the above expression. Got? Let us see two examples. Example number one. So this was the rise of the liquid, right? This was rise, capillarity, and there was a rise of the liquid in the tube. So let us see example one. So suppose I have a liquid like this, okay, liquid, and I have two plates like this. Eventually, some liquid will rise till here, okay, in between the plates. Okay. Some liquid will rise till here. Okay, are you able to visualize? The liquid has risen up till here. So let us say the height is h again, till which it has rise. This is height h. Again, there is a meniscus at the interface. A meniscus will form, and again it will have sigma, vertical and horizontal components of that sigma. So vertical component sigma cos theta, sigma sin theta. Here also it will be sigma. So sigma cos theta, sigma sin theta, sigma cos theta. Okay. And this sigma is acting like this, liquidly. Okay. The vertical component, sigma cos theta, sigma cos theta, sigma. All the horizontal are balanced and vertical are sigma cos theta. Okay. And let us say the thickness of this between these plates is T. Okay. Again, this risen up has some weight which is acting I'll use some other color. This will have some weight, whatever the liquid has risen up. So again, we will see what is surface tension force Fs is nothing but sigma cos theta, and this time L will be left interface and the right interface. Okay, so it will be 2 times of L. 2 times of L. And what is L? This is your length L. 2 times of L. It is 2 sigma cos theta L. Okay. Whereas weight will be specific weight into volume. That is W into what is the volume? It is length into H into thickness. Length into H into thickness. Okay. Again, length into H into this is the volume of the cuboid. That is length into H into thickness. So this is the way. Now you will balance for equilibrium. Weight is equal to the Fs. W into L into H into T is 2 sigma cos theta. Okay. This L and this same capital L. This L get cancelled out. So H is the important thing. That is 2 sigma cos theta by W. It's a very important expression. You know what is the width between, what is the thickness between them? You know what is surface tension coefficient? You know what is the angle theta? You got what is the vertical rise in the H. Okay. Okay. So H is again here. H is inversely proportional to T. Lesser the diameter, higher the mass. The diameter. Earlier it was cylindrical tube. This time 2 plates are there, which has some gap of mass. Another scenario, example number 2, where you have like a tube like this. And it is a hollow from like this. This is dipped inside a liquid. The outer diameter is d naught. Inner diameter is di. Again, there will be 2 meniscuses. It's around whole of the circumference if you visualize from the top. It is not just 2 meniscuses, it's outer and the inner. So again, it has risen up to, this is liquid, risen up to some H height. Again, we need to see, and this is solid glass. This is complete solid glass. So follow. So hollowness is inside this region. So solid glass. Again, it will show some wetting scenario. So surface tension sigma will act again. Sigma. Here also sigma. Sigma. Okay. So one surface tension is acting on the outer diameter, sigma into pi d naught, surface tension force, and in the inner diameter, sigma. And there will be weight acting. Weight is acting. This is not 2 times of weight. This is a single weight only. Just to represent that, I'm showing like this. So surface tension force, if I draw this again, surface tension force is again sigma cos theta only, as well as inside also. This is sigma cos theta. And outer diameter, make sure that it is less than 10 mm. Okay. And this is a hollow glass. So surface tension force is sigma cos theta into L, that is pi outer circumference, plus sigma cos theta into L, that is pi inner diameter. So that is sigma cos theta pi into d outer plus d inner. That is your surface tension force. Similarly, weight is nothing but specific weight into volume. W into what will be the volume of this hollow glass? Pi by 4 d outer square minus d inner square. This is the volume. Simple from this perspective. This can be written as pi by 4 from a square minus b square, a plus b into a minus b. For equilibrium, you compare them. Weight is Fs, so it is W into pi by 4 d outer plus d inner into d outer minus d inner is equal to sigma cos theta pi into d outer plus d inner. This gets cancelled with this scenario. So your final height h, pi by 4 d square h, sorry, h I have missed, pi by 4 d square h. So h will come from here, that is 4 sigma cos theta by omega into d outer minus d inner. Very important. And if your d outer and d inner are same, or sorry, if d inner is 0, then it is the same as the first expression, that is 4 sigma cos theta by WD naught, WD, 4 sigma cos theta by W. Okay. Similarly, if you do for a tube kept in a mercury, for a tube kept in a mercury liquid is mercury, then there will be not rise, there will be fall. For Hg scenario, if you have a beaker like this, okay, filled with mercury, your tube is like this, there won't be rise, there will be fall. So liquid is still here. This is Hg, and this is glass. And how much the liquid has dripped by a height of h, dripped by a height of h. Again, there is P atmosphere which is acting. Inside, a higher pressure will be there eventually. The meniscus, P, okay, and here it is acting P atmosphere. The meniscus is like this. Again, surface tension direction will be this time like this on the meniscus, sigma. This on the meniscus. So if I want to say what will be the change in pressure at the meniscus level, delta P is nothing but P minus P atmosphere. P minus P atmosphere. And P will be, what will be the P at this point? P atmosphere plus rho gh. P atmosphere plus rho gh. P atmosphere plus rho gh minus P atmosphere. The change in pressure is nothing but the hydrostatic pressure, that is rho gh. And you don't know what is height h. So what you will do, you will again balance through Fs with weight. So this was your meniscus. This is your meniscus. This is the surface tension, which is force, which is like this. So here this time the angle will be, this will be the angle from, if you draw the tangent from liquid to the surface. So this is your angle from liquid to the surface. This is theta. Okay. So this is theta. This is theta, and this will be how much? Total it is 180 minus theta. So this angle I'll just redraw once again. If your tangent is going like this, and you take the vertical component, sigma, this angle will be 180 sigma cos of 180 minus. Okay, around the whole thing. Balance for equilibrium, weight is equal to Fs, or you can say pressure force, that is not weight. This time we are balancing through pressure force, Fp. What was Fp? Delta P into pi by 4 P square is equal to what is Fs? Sigma cos of 180 minus theta into pi into P. So from here H will be same, again same as per the rise, but only differences of the negatives, 4 sigma cos theta. Right? So just remember that if rise is there, it is 4 sigma cos theta by WD. Whenever there is a fall, just put the reverse. So always solve with the rise. Try to solve with rise and just put a negative. Okay. All right. We are ended with the chapter fluid properties completely, and we'll start with hydrostatic part. Okay, pressure measurement. There we will deal with pressure measurement chapter. So I expect that all of you are regular to your statements. Those who want to see you get the Nptel recording sheet where all the links are there. This session is recorded. You can see all the links in that sheet. I'll upload this video as well on my YouTube channel. My YouTube channel name is Nptel with Varnit. Okay, and this PDF notes will be in the group description, video description as well. The link to the Google. All right. Any other doubts to anyone? Or we can end the session, please. Okay, so I'll see you on the next Tuesday, same time, 6 to 8. Bye-bye.